Good afternoon, ladies and gentlemen. We are very pleased to see you here today, the open days of CERN. My name is Marcus Nordberg. I was asked to tell you a slightly different story of what we do here at CERN. Not about the what, but rather the how. You've seen and hopefully actually visited many of the scientific locations here, and you may have already heard many stories about the size of it, the shape of it, the astounding performance of it. And then maybe you have been told that there's about 3,000 people working for one experiment alone, and that we have actually 4 of them, at least linked to the LHC. Maybe you have asked yourself, how is it possible that these many thousand people can actually come together to work from all different parts of the world together here at CERN? So that is what I'm going to tell you about. And I will focus on ATLAS experiment. That is the experiment I have worked for the past 12 years. I'm a proud member of the ATLAS experiment. Until recently, I was in charge of the financing of it. And so I will be talking about ATLAS because I simply know it best. But it is very similar to any other, at least of the 4 experiments. There's CMS, ALICE, and LHCb, in addition to ATLAS. So I hope you are not too upset that I only talk about ATLAS, because in terms of structure and the way people work together is very similar. Now I have to find the clicker. I forgot to pick it up. Here we are. All right. These are my conclusions. There is no way I can explain 30 years of work in 25 minutes. So I thought, to be on the safe side, I'll just give you the summary now, and then if I have more time, I will expand upon it. So these are the 3 things I wish you to remember when we talk about scientific collaboration. First is vision, second is commitment, and third is tolerance. Now, interestingly, we don't use this sort of jargon here at CERN. If you walk here at CERN and you stop a physicist and say, "Hi, can you share your vision?" They will probably look you a bit strange and say, what are you talking about? This actually comes from a set of studies that have been carried out here at CERN. Our colleagues from different fields, like we have an anthropologist here. She actually gave a talk earlier today. We've got business management scholars. We've got psychologists. We've got people from social science. We have economists. And they have been looking at it for the past years. Sometimes we feel that we are a bit like monkeys in a cage. They give us a banana and ask us to jump up and down. And we do that happily if we are helpful for them. And they think we are. And they are very intrigued by these questions that we usually don't ask ourselves. How is it possible such large collaborations work? And how do they work? And why do they work? So these are the quick key things. So let's start with the vision part. So in a summary, we would say that we like to do things that nobody else can or wants to do. So very, 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 very ambitious tasks, like understanding the universe. I mean, universe is a big place. You have heard already presentations that going, to the visible size of the universe, and then zooming in all the way to the very beginning of our universe in terms of the Big Bang, is all one and the same thing. It's a huge, 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 huge research task. So we have taken upon ourselves to try to understand that. Specifically, we try to understand how our universe began. And if you take a philosophical point of view, what is the role of us as individuals in this huge cosmos? The second point is commitment. Don't forget, I mentioned already 30 years ago, people in these experiments started to think about this. We have been running these big experiments since 2008-9. We're just at the very beginning of this very exciting adventure. There's still at least 15 years to go. So people commit their full professional lives to work in these large experiments, to understand what the Higgs is all about. But not only the Higgs, there are many, many other exciting discoveries that we will be expecting to be making in the next few years. The last is tolerance. Now, tolerance can refer to many things. And of course, here at CERN, we're very proud of the mechanical tolerances. When we build these big devices, we know that it has to be accurate over several meters, let's say 10 meters, with an accuracy of 1/1,000,000th of a meter. So that's very, very accurate. Another way of putting it is that the devices that we use are so sophisticated that if we would use it for, let's say, measuring snowflakes, we could actually detect when a snowflake hits the Alps. We could see the change in the weight of the Alps. Or if we would use it as an optical telescope, we could actually turn it, if we turned it towards the planets, we could actually see a grain of sand on Neptune. So these tolerances, either mechanical tolerances or scientific tolerances, engineering tolerances, are extremely high. But that's not what I'm talking about. I'm talking about human tolerance. We have people from over 50 different countries. I can't even count the number of languages in the CERN main cafeteria. If you have a chance to go there, I hope all my colleagues are sitting there, because it is very revealing just to walk through the corridor and listen to the buzz and listen to all these different languages. It's quite exciting. Also, in terms of diversity, we love diversity. We very much like to talk to people coming from different type of cultural background, religious background. What brings us together is the joy of science, these audacious plans that I've already mentioned. So let's go a little bit. That's basically what I wanted to say, but since I still have time, let's go and try to understand a little bit in more detail what I just said and put that in context. What's wrong with this picture? This is a picture actually that Pauline showed a moment ago. I don't know if you were in the room, but she showed this picture and explained it in a very nice way. Basically, this is an artistic interpretation of light coming from stars, light coming from galaxies, and it's a pretty picture. But if you would take the science behind it, all the data, and if you would use other types of measurements, which I don't have time to go into, you might be shocked to hear, as Pauline was telling you, that we can only see or measure stuff, that is mass energy around us, less than 5%. 3.5 to be exact. 3.5%. Now, let's put that in perspective. That is to say that we can only understand 3.5% of the mass energy around us. And this is not somehow, a question of somewhere in the deep space. No, it's in this room, for example. It's not 96.5% of disappearing mass somewhere in a remote galaxy. No, it's right where we are. So when I push my hands towards you about a meter, the stuff that we can actually explain using experiments here at CERN, for example, is a few centimeters. So what the heck is the rest? And where is it? This is the type of question that keeps us awake. And every morning when we wake up, we get on our cars and bikes and motorcycles and, pedal along to CERN with great excitement. This is these type of questions. Now, how would you explain this? So we have a problem. How could you explain it? Well, there are theories, many theories. One of them is that there could be more dimensions than the 4 that we live in. So you know the 3 very well. So speed, width, height, and length. But there's also time. That came from Einstein's theory of relativity. So technically speaking, we comfortably work in a world of 4 dimensions. But what about if there are more dimensions than 4? Maybe there are 5, 6, 7, 8, maybe even 11. What would that mean? Just imagine if all this stuff that we can't see is actually somehow filtering through or dwining through these dimensions that we can't see. Think about that for 1 second. If really there would be more dimensions around us than we perceive there are, what would that mean to us? Would that explain things better? Would it make our life more complicated? I don't know for that, but I certainly tell you it makes our life a lot more exciting. And just the perception of being able to enter new universes is quite spectacular. And if you take those theories literally, physics theories do offer the possibility that we live not only in this universe, but in many, many, many universes. So when I again push my hands towards you, there may be thousands of different universes where we all exist, but slightly differently. In one universe, instead of me standing here and talking to you, this will be empty. In another universe, you may be standing here giving the talk, and I will be sitting where you are. And the different permutations, all these. So each universe would be slightly different. It is this type of thing that makes us very excited. It is this type of thing that brings us together to work together in large numbers of people. How do we do this? What is the process of setting up a collaboration and designing an experiment? So first we start with the physics. So we rely on our very clever theoreticians who think about these sort of things. This is Peter Higgs. He's laying out the famous Higgs field that you've heard so much about. I wish to emphasize there are many, 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 many other type of interesting fields and many, many other types of interesting particles that we are looking for. The fact that I'm talking about Higgs, that you know that we've found the Higgs, at least seen observations of it, doesn't mean that there isn't anything else. Far from it. This is just the very, very exciting beginning. Anyway, here's Peter writing this equation, and that basically starts the machinery. We start to look at that machinery, that equation, and start to think to ourselves, how can we turn that into something measurable? And we know that we need something to generate huge amounts of energies in a small area that we can then look into. And this is where the accelerator comes in. You've seen and heard about the Large Hadron Collider. It's a beautiful machine. What it does, it accelerates protons and protons in opposite directions, like two cars in a racetrack. And that racetrack goes around, as you know, 27 kilometers around here at CERN. And we make these particles to collide in 4 specific points. These points are the experiments I mentioned. One is ATLAS, CMS, LHCb, and ALICE. How do you design an experiment? So now you know what you want to do, so you have to start the process. And what you do is you use a lot of computing. You've heard stories about the massive computing capacity that we here have at CERN and elsewhere. And we use this computing power to simulate things. So we actually try to figure out all possible permutations of the collisions that these 2 racing cars, these 2 proton beams would generate. And we analyze them very carefully, and then we store them. And then what we do, based on this, we try to make a visual representation how that physics equation that I just showed you, the Higgs equation in this case, would manifest when we would design equipment around it. So you can see here in this picture these particles going in different directions. And in order for us to see those particles going in different directions, all this other stuff here around needs to be designed and manufactured. There are different types of technologies that are needed to be done that. So we get involved in that. We start to design everything around that collision point so that we can make these particle tracks visible. That is the task that this large group of people will be doing and has done. Then, of course, you get the engineers. The engineers come in and they look at this device from an engineering perspective, of course, very closely working together with the physicists. And they look at it from an engineering perspective. I've shown you the physics equation. This is the way the engineer looks at this picture. So in this picture, there's about 3,000 kilometers of cable. There's about 100 kilometers of copper cable. There are all sorts of mechanical support structures there, you know, gases, water, all this optical cable, stuff like that. It has about 15 million functional components. Put that in perspective, a jumbo jet has about 3 million. Space shuttle had about 6 million. This is a very, very complicated piece of work. I was once told by a Navy official who, came to see us, just passing by. He said, this is as complex as an aircraft carrier in the US Navy. I don't know, I have never counted the components on the aircraft carrier, but this is what he told me. And this is what you get. This is a picture of Atlas seen from below. And I don't know if you can see from this picture, but actually there's a guy here, a chap. He's there. Just to give you the size, this is about 46 meters in length, 23 meters in diameter, weighs about 7,000 tons, as much as the Eiffel Tower in Paris. If you have the opportunity of seeing CMS, remember it's a bit smaller, but it's twice as heavy as Atlas. It's 15,000 tons, 2 Eiffel Towers. So these are big, big devices. And this is the process that this collaboration has gone through. And there are all sorts of nice technologies involved in this. I don't have the time to go in, but just to give you some highlights. So we have different types of technologies, semiconductor-based technologies. We have optical technologies. We are using techniques that take devices to very, very low temperatures. A large mix of different types of techniques, different types of people. That explains why we have a large community, because we need all that expertise. If we don't have this expertise in our own labs and our universities, we always work together with other laboratories and university departments within our university network, and that has been quite successful. Now, how do you put this all together? There is this myth, and certainly those of you who have read business management, there's always this myth about this Superman or Superwoman who somehow woke up one morning and had this brilliant idea. I had a dream. And usually this is a CEO of a big multinational company. And this president or CEO says, we need to find the Higgs. My life is really, I've seen the light, and I really need to get this Higgs on the ground, so I'm gonna set up this collaboration. And then what he does, or she does, gets a sort of group of people that he or she trusts and says, guys, I wake up this morning and I had this great vision. We're gonna build a big detector and a 27-kilometer accelerator, and we're gonna bang the matter together and we're gonna make these wonderful new particles. And all these guys say, yes, boss, yes, boss, yes, boss. And then, of course, what they do, they have to enlighten the staff, the workers, okay? So off they go, and they enlighten the workers. The boss has a vision. You better follow. Either you join us or we fire you. It's very simple. And by and large, in companies where you make, cameras or shoes, it works. And then, of course, then you make strategic plans. They're very good at, making, we're going to do this, and then we're going to do that. And of course, the first thing they do is compartmentalize everything. So you make an organigram, and of course, the boss is always sitting up there, and then everybody else sort of filters down. And of course, we put them in divisions to make sure that the work is divided, meaning that they don't talk to each other, and then they basically wait for a miracle. Well, this is not the way we do things. And of course, then you do the deal with the customer, and everybody's very, very happy and goes for a glass of champagne. Well, this is not the way it works. In fact, in our environment, it works a bit like a high-tech picnic party or a potluck party, which means that a group of people casually get together who have this idea of trying to visualize, in this case, Higgs's equation, in a way that we could actually build a device that could see and identify these different reactions and then lead to the discovery of the Higgs. And this starts with people. I'm sure you have never seen these people, or most of you don't know these people. And probably you'll never will. But these people here, as an example, are heroes. These are the people who spend their lifetime in trying to figure out how they could find all these exciting particles and try to understand and unravel the secrets of the universe. And they get together. They have a kind of a discussion. Here it is actually a sort of a picnic. And the job of the collaboration is really to make sure that the partners who come into this collaboration voluntarily provide input in terms of knowledge or equipment that can be put together in a coordinated way. That is how it works. It's a bottom-up approach. And we actually have a document that lays this out. We call it the Memorandum of Understanding. And it's a very simple document. It's only 7 pages, roughly, in its essence. And what it says, in simple terms, is that this is a kind of as I said, a picnic party. It's on a voluntary basis. It's not a legal commitment in any way. Actually, the document says very proudly on the cover page, this is not a legally binding document, which thrills my lawyer friends because they don't quite agree with that, but it works very well. And this simple document says, okay, everybody who joins this picnic party will provide what we call deliverables. This is a set of equipment. They build it in their own labs together with the industry, and then they ship it to CERN. And all this stuff comes, in the case of Atlas alone, from 38 different countries, from 177 different universities, including, as I said, over 3,000 people. And then, since we are very simple folks, we don't kind of really worry about, physicists don't know much about inflation. So we forget about inflation. Physicists are not very good with the exchange rates. They are difficult, so they just fix them, okay? And then they just go on about it. And the big surprise, as I was involved in that process, it really works. How is it possible that so many countries, so many people can build this stuff which works based on so few simple rules? But it works. And I would like to emphasize that this is a community that elects its members into position, if you like, of coordination. We don't have any managers in Atlas. They are all called coordinators. And as I said, I was the one who was taking care of the money for 12 years. So we rotate. Now there are new people in place. And that's the way we work. So very, very different from the classical view of top-down. First you have the CEO, and then you have his lieutenants, and then you have all the little workers. It's really the other way around, that the expertise is on the ground level, if you like, with all these people that you possibly have never heard of. They are the ones who have made Atlas and CMS and LHC B and ALICE possible. Here's an organization structure. This is a very simple structure. Basically, you have a parliament up there. It's to the left upper corner. We call it collaboration board. It consists of all the institutes are involved. Then you have the coordination mechanism, which is the spokesperson, not a CEO, but a spokesperson, with his or her team. And then you have all the projects below. And they all form this executive board. And this red blob to the right is the body that we talk about, resources and money, with all the governments that participate in these experiments. It's very simple. It's not complicated. Now, the way we go about this is that we go from design to the construction, and you can see that it's kind of messy. And this is an interesting assumption, at least when I talk to my friends in the other business fields and so on, that they always give the impression that it's very nice and easy, it's all linear and so on. Well, it ain't. It's very complicated. We are actually trying to solve problems that we don't quite know. Don't forget that Atlas and CMS and the other two experiments were designed roughly in the mid-1990s, based on technologies that did not exist at that time. That technology that we have since developed is still there. It's still at the cutting edge of technology for the next maybe 5 years to go. But at the time when we designed it, it didn't even exist. So we have to take these leaps. I mentioned to you earlier, we take a sort of a leap of faith almost, an order of magnitude jump, not from version 1.1 to 1.2, but from version 1.1 to 10.1. And it's a huge, huge jump. And we organize ourselves in way of clustering around the technologies where the people don't come through an organic run, but they join those specific projects where they think they can contribute most. And that's the way we work. And sometimes we do it wrongly. If there's a problem we can't solve, then we have to go back. I once gave this presentation and somebody noted, Marcus, your physicists are going back in time. I said, that's an interesting notion, because technically speaking, that is exactly what we do, if we have to. If we can't figure out the design based on approach that we started with, we will go back. We will go back to the drawing board and start the process all over again. And we will find a solution to the problem. If we can't figure it out within our community, we will go to our friends and colleagues in the engineering departments, and of course to the industry whenever needed. And we are global. This is Atlas, but this will be exactly the same for CMS and ALICE and LHCb. You can see some areas here. Everything which is in yellow means that they are part of Atlas, and you can see that it is pretty much global. Somebody once said jokingly that in Atlas the sun never goes down, and it's true. There's always somebody working on Atlas around the world, and like in CMS. So this is what you then get. When you put all this effort together, you get a detector. This is the picture that I showed you a moment ago, seen from below. And it's a conceptual device, and this is the end result of this process of getting all these people together. But of course, this is all about people, and here is a way of nicely showing it, that we have divided this matrix into pictures. Actually, this is from the database of all the Atlas members, so if you have a magnifying glass, you will probably find all of us there. And this is another picture of the collaboration. We meet 4 times a year, so this is taken from one of our meetings. Of course, there are not 3,000 people. If everybody would come to CERN in one go, we would be really in trouble. CERN could not host 6,000 visitors in one go. Anyway, I'm the third guy from the left, so just to put that in perspective. And what we are very proud of is that whatever your contribution to the experiment is, you will always be recognized. So let me put that. So we have in all the physics papers, everyone who contributes in Atlas gets his or her name in all the scientific papers that come out. So let me show you something that I treasure. This is a paper that you can publicly download. It's free of charge from the internet. This is the discovery of the Higgs. This is what has made so much excitement. We are very excited. I wish to emphasize this is just the beginning. This is not the end. But this paper, for me personally, is very, very precious. It combines the results of Atlas and CMS, so it has about 60 pages in total. And if you would care to open it, and I will now do it for you, there is the first article is about Atlas, and it goes on explaining about the discovery for about 30 pages. And then starts the authors. Author page number 1, author page number 2, author page number 3. I'm here, author page number 4, okay, and 5. Wonderful. Everybody who participates. I paid bills. I never even came close to the Higgs discovery. I was sitting in my office paying bills. But I'm part of it. And I think this is one of the most motivational things. This is one of the things that makes collaboration tick. If you participate in it, whatever your contribution has been, you will be recognized. And that's a very powerful incentive. It's an intellectual one, but it's nevertheless very important. This makes the world tick. So I'd like to come to the end of my presentation, and here you see the slide that I started with, my conclusion slide. So what Atlas is really about, it's about stories. It's about people who care. There are many stories I've collected here. I don't have the time to go through them. But I just want to try to assure you that this is about people who really care, people who are putting most part of their scientific professional life into one experiment to make sure that whatever they do will be for the success of the experiment. And there are people, there are stories. There's, for instance, here, there's a lady who is pulling She's a physicist, one of our top physicists, and at that time when we were building Atlas, she was pulling cables. She had a cable team of about 10 people here. And with these people certainly had better things to do, but they took upon themselves this task of pulling all the many, many thousand cables that are needed in one of the subdetector. And they did it very, very well. When it was switched on, it worked without any hiccup. That was a remarkable achievement. Here we have a guy here who ran a team. He is proudly showing a picture of two of his colleagues. One is from Israel, the other one is from Pakistan. And he was leading a large group of Israeli, Pakistani engineers to put together a very large piece in Atlas. And in fact, the group is over there to the upper picture, to the upper right, and they got to work together. Now, you may understand the difficulties in getting people from different parts of the world to work together, but this guy here was very proud that he made a contribution. He felt his biggest contribution was to get the different people, type of people, to work together. And then there are many, 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 many other stories. But the delight and the joy and the commitment and the vision is everything that has made these experiments work. And I'd like to finish with one slide which has to do with the grid. This is a tool that we use to distribute all the information from the experiments to many, many, many countries where it's analyzed. And there was a presentation just before me about that. And the way these projects, which we now call e-science projects, work are very, very similar to the way Atlas and CMS and the other experiments have been built. Now, of course, what we do here is physically linked to an experiment which is 90 meters below ground. So Atlas is, in fact, just outside this building. When you leave the building, if you see a mural with a nice painting, that's where Atlas is, 90 meters below that painting. But the way it comes together, and e-science projects that you may have heard of, which are doing computer-based significant things, these are very similar in structure. And in fact, they are much inspired by the way we do collaborations. And my personal hope and wish is that there will be one day a Facebook project like Atlas or CMS, a Facebook project that you can participate in to make something fantastic and contribute your time. You don't have to be the expert, because what is needed is time and effort and concentration. This is 99% is hard work. 10% or 1% is then the glory that comes later, but it's hard work. And I hope that these type of experiments we will be seeing in Facebook or in another form that you can participate in. And these projects, with some guidance, as we do here at CERN, gentle guidance, will produce fantastic papers that will change our world. And that's why it's so exciting to be working in a place like CERN. Thank you very much for your attention.